All right, let's dive into the origin of the computer. It's a story that I guarantee begins much, much earlier than you probably think. So let me just ask you, when do you think the first computer was built? Go ahead, get a date in your head. You're probably picturing, what, a massive, room-sized machine from the 1950s? Maybe the 40s? With all the punch cards and vacuum tubes, the whole deal? Well, what if I told you the answer is actually more than 2 millennia ago? That the first known analog computer was clicking and whirring away while the Roman Republic was still at its peak?
Yeah, that's where our story begins, with a device so incredibly advanced for its time that its complexity wouldn't be seen again for over 1,000 years.
Meet the Antikythera mechanism. It was discovered in a shipwreck, and it is an absolutely astonishing piece of engineering. This wasn't just some simple clock. You'd turn a hand crank, and through this incredibly complex system of at least 37 interlocking bronze gears, it could predict the movement of the sun, the phases of the moon, and even forecast eclipses decades in advance. It could even track the 4-year cycle of the Olympic Games.
When sponge divers found it back in 1901, its true purpose baffled scientists for decades. But the most incredible part of this story is the timeline. After the Antikythera mechanism, this level of mechanical complexity just vanished. It didn't reappear in another machine for almost 1,500 years. It was like a technological path that humanity started down and then just completely lost. And this timeline just perfectly illustrates that massive, massive gap. From this ancient Greek marvel, we have to jump forward nearly 2,000 years to get to the next monumental breakthrough. The story really picks up in 1946, right after World War II, a conflict that had created this urgent, unprecedented need for super high-speed calculation.
You see, the next great leap wasn't just about building faster calculators. It was driven by a completely revolutionary idea about what a computer could and should be.
So here's the game-changing idea, the stored program concept. It was most famously laid out in John von Neumann's 1945 first draft report. Before this, a machine like the ENIAC had to be physically rewired, literally unplugging and replugging cables to do a different task. The new idea was that the instructions, the program itself, could be stored in the computer's memory, right alongside the data. This is what made machines flexible, powerful, and, well, what we think of as a computer today.
And this idea hit the world's top engineers like a lightning bolt. A British scientist named Maurice Wilkes read the report on the boat trip home from a series of lectures in the US. He later said he knew instantly that this was the future, that this was the realization of his dreams. He got off that boat and immediately started designing his own machine.
But there was a problem, a big one. Everybody now knew what they wanted to build, but a critical piece of the technology was missing. This whole stored program idea needed a fast, reliable memory to hold both the program and the data. And in 1946, that just didn't exist.
So 2 main ideas emerged. The first was called serial access memory. It used these big tubes of mercury to store pulses of information, a really clever bit of tech borrowed from wartime radar. But it was slow. You had to read the data in the same order you wrote it in. The real holy grail was random access memory, or RAM, which would let a computer jump to any piece of data instantly. The only problem? No one had actually invented it yet.
And this is where the British took a surprising lead. Their engineers, many fresh from top-secret wartime projects like the Colossus code-breaking machines, had this deep well of practical experience. And at Manchester University, 2 guys, Freddie Williams and Tom Kilburn, they cracked it. They figured out how to create a working RAM using a cathode ray tube. It became known as the Williams-Kilburn tube, and it basically won them the race. And get this, the race ended with a pretty stunning result. By the beginning of 1950, there were only 3 operational stored program computers on the entire planet, and all of them were in Britain. Despite all the huge efforts in the US, they had 0. The British had won the first critical leg of the computing race.
Okay, so the pioneers had built the hardware, but this created a new, really fundamental problem. How can a machine that only understands on and off, just binary ones and zeros, how can it handle complex math, especially negative numbers? Well, the solution is a surprisingly elegant little mathematical trick.
It's called 2's complement, and it's basically a clever way of reinterpreting what the binary patterns mean. So for example, the pattern of 1s and 0s that normally means 9 suddenly means -7. This clever remapping lets the computer perform both addition and subtraction using the exact same circuits, which is just incredibly efficient.
So here's the magic behind it. The very first bit isn't just treated as a plus or minus sign. Instead, it's given a negative weight. So in an 8-bit number, you have bits that stand for 1, 2, 4, 8, and so on up to 64. But that very first bit doesn't represent positive 128. It represents negative 128. And from there, all the math just works.
Okay, I know. That's a pretty deep dive into computer science theory. But why does this abstract math actually matter in the real world? Well, because when it goes wrong, the consequences can be absolutely catastrophic. In 1991, during the Gulf War, a U.S. Patriot missile battery failed to shoot down an incoming Scud missile. 28 soldiers were killed. The cause was a software bug that came down to this exact issue. You see, the system tracked time in tenths of a second, but the fraction 1/10 in binary is an endless, repeating number. The computer's 24-bit register had to chop it off, creating a microscopic rounding error. But after 100 hours of being switched on, that tiny error added up to 1/3 of a second. And in missile defense, 1/3 of a second was enough for it to miss its target by half a kilometer.
So this brings us to the incredible legacy of those post-war pioneers. The architecture they designed, the mathematical rules they relied on, they are still with us today, forming the very bedrock of our digital world.
And this is it, the von Neumann architecture. It's the essential blueprint that came out of that revolutionary period. It defines a computer's 4 core parts. You've got memory to hold programs and data, you have input and output for things like your keyboard, a system bus that acts like a highway connecting everything, and of course, the central processing unit, the CPU, the brain of the whole operation.
And here's the most astounding part of all. That simple, elegant blueprint from the 1940s is still the fundamental architecture inside the super powerful smartphone in your pocket right now. The components are billions of times faster and smaller, of course, but the basic design, the core logic, is exactly the same.
So, from an ancient Greek calculator all the way to a single rounding error with tragic consequences, the story of the computer is an incredible tale of human ingenuity. The blueprint for our entire digital world was drafted over 75 years ago. It really makes you wonder, what will the next revolutionary blueprint look like? And when will it finally get here?